Welcome to another video, everyone. Today we're going to be covering gravitational fields from A2 physics. So first I want to start off with defining gravitational field strength. So this is sort of the basics that we start off with, and this is a very important concept even though it's simple. So gravitational field strength is defined as the force per unit mass. And as an equation, you can write it as F over m. So the force per unit mass. And then the SI units would just be n kg to the power of -1. Now something to remember is this is a field. So when you're saying fields, when you're talking about fields, you're automatically defining them as vectors. So the gravitational field is a vector and is defined by field lines. And then here you can see the higher density of the lines means that the region of field is stronger. So the more dense your lines are compared to, for example, this, so this will obviously be a stronger field. The region here would be stronger than the region here. So that is basically what gravitational field strength means. Now Newton had come up with a law of gravitation, and that is defined as the force between two masses is proportional to the product of the masses and inversely proportional to the square of their separation. All this law is basically saying is putting into words what this equation tells us. So as you can see, the force between two masses is proportional to the product. So G here is a constant. It is called the gravitational constant, and it's defined as 6.67 times 10 to the minus 11. So when you say that the force is proportional to the product of masses, we can say this because G is constant. So we would have F proportional to m1 times m2. And we would have the same thing for R, except R would be inversely proportional because it's 1 over R squared that is proportional to. So force is inversely proportional to the square of its separation, which is R. So the way to visualize this case is if you have two masses, m1 and m2, the R would be between the midpoints of the spheres, and so this would be R, that distance. So the force between these two masses, the gravity that acts between them, is proportional to this the product of these two masses, and inversely proportional to the square of their separation R. So that's basically what this equation tells us. It gives a relationship of the gravitational force between two masses. And one thing to remember is gravitational force is always attractive. Unlike forces like electric force, where you have a positive and negative, you know that like charges repel, unlike charges attract. But for gravitational force, so far we've only observed attractive forces only for gravitational forces. And here is a visual of gravitational forces. As you can see, the Earth is a huge sphere, which I've only drawn the surface of. So you can see here, these are the field lines of the gravitational force that comes about from the Earth's mass. So every mass gives off a gravitational force because every mass causes a gravitational field. So the way this gravitational field can be drawn is in towards the mass. And one thing to specify is that when you have a really large mass such as the Earth, if you look at the surface, it would approximately be parallel. These radial lines, if you really zoom out into the Earth, then you would see these lines are radial because they point towards the center of the sphere. But when you are on Earth, since the Earth is such a huge sphere, this approximated to just parallel lines. So if you really zoom in into a surface of the Earth, these field lines would approximate to be parallel. And when you have lines that are parallel and equidistant, that tells us that the field is constant and uniform. So, of course, in such a large scale, these field lines are not parallel and equidistant, so you would not say that the field is constant in such a scale. But when we are only looking at the Earth, on the surface of the Earth, and we're doing calculations with those, then we approximate it to be approximately constant, and that is where the number 9.81 comes in, because that is the gravitational field strength. It's approximately constant on Earth. That's why our calculation with 9.81 works on the surface of the Earth when we're doing classical mechanics on the surface of the Earth. So that is a common exam question that you should probably remember is why the gravitational field strength is constant. You would say that Earth has a really large radius, so that will be your point 1. So you approximate the field lines as parallel and equidistant, that's your point 3. And if the lines are parallel, that means field is constant or uniform, so that's your point 3. Okay, now let's see what we can do with some equations that we know already. So we know the very common Newton's equation from IGCSE, F equals ma. And now we've also learned for an equation for force between two masses, which is F equals gmm r squared. So you can either write it as big M or small m, or you can write it as m1, m2, any way is fine. All you have to show is that these two m's are not equal. So if we combine these two, since the force here and the force here that we're talking about is the same, we can sort of rearrange for A and write it as A equals F over m. And then we sub the F here into this F here, and we get A equals gm over r squared. Now this is the acceleration due to gravity. So the acceleration a mass experiences due to the gravitational field on the Earth. So this can be the same as the gravitational field strength on the Earth, because the acceleration is only experienced due to that field strength. So A and G, which is the gravitational field strength, are equal. They're equal. They're both 9.81. But when you are, for example, deducing them as units, then you really need to be careful what you are referring to, the acceleration caused due to gravity or the gravitational field strength. If you're talking about the acceleration, then obviously you would use the units of ms to the power of -2. If you're using gravitational field strength, then you would use the units of n kg to the power of -1. So you really need to see the context of how you want to explain things according to whatever the exam question is asking. So here is again something that I've written down. What is the difference between acceleration due to gravity and the gravitational field strength? Well, they are the same number. They are both constant, 9.81. But when we define these, we define them a little bit differently. The gravitational field strength we define as strength of gravitational field at a point, which is the gravitational force applied on the body at that point. So it's the field due to the gravitational force applied to the body at that point. But acceleration due to gravity is the acceleration felt by the body due to the resultant force applied to the body at that point. And the resultant force in this case is the gravity acting on the object because of the Earth. So I hope you can see how those two link and the difference between them. Next, what we're going to look at, now that we have our basis of what gravity is and the gravitational field, we're going to add another layer of knowledge to it and define gravitational potential. So gravitational potential is defined as the work done per unit mass in bringing a small test mass from infinity to a point. Now, what does this mean? So if you have, for instance, the Earth, let's label this as E, and you have an object that is so far off that we say as a concept that it's starting from infinity. So infinity really isn't a actual thing, it's just a concept that we say just to sort of visualize it being so far off that it's not affected by any forces. So if this object is coming down to the Earth from infinity, it's coming down from infinity, then you can see here that the Earth, I've drawn it here as well, the Earth's gravitational field is going inwards. So the work done to get this point towards the Earth would actually be negative, because you really don't have to do any work. The field is doing the work for you. It's basically helping you get that point there. So you're not really acting against the field, you're acting with the field. So that's why the work done would be negative, because you don't really have to do any work. You have to do negative work to get this point to the Earth. So that is why gravitational potential is actually defined as negative. And if you see the equation here for it, this is a symbol for gravitational potential. It's negative gm over r, and these are the SI units, so remember those. So all you need to remember is the gravitational potential is the work done per unit mass into bringing a small test mass from infinity to a point. And the reason why it's negative is because there is negative work done to bring that point from infinity to the mass. So another way to, some other formulas of gravitational potential that you can write is the electrical and the potential energy, so the gravitational potential energy divided by the mass is equal to the potential. So all the energy is work done times mass. So if you divide by the mass, then you get the work done, which is the gravitational potential. And another formula is potential equals GH. So where does this come from? So the work done is the change in potential times mass. Now if you define the work done as the gravitational potential energy, which is mgh, and then you can equate it to the change in the potential times the mass. And when you cancel the m's out, all you get is the change in potential is equal to gh. And so we say G, which is the gravitational field strength, is the change in potential divided by the change in height. So this is a very important formula as well. So now that we know the concepts and the basics of gravitational potential and the gravitational field strength, let's look at how energies relate to all of this. So we know gravitational potential energy is mgh, energy caused by opposing the gravitational force. So what we can say is m equals potential, since we know gh is potential, as we found from this formula. So we substitute potential for minus gm over r, remember why it's minus, and we get minus gmm over r for the equation of gravitational potential energy. Now we can also deduce an equation for kinetic energy. And now this kinetic energy is coming from the centripetal force and the gravitational force equated together. So if you have the Earth here, and you have an object here orbiting the Earth, the centripetal force, due to the circular motion, is equal to the gravitational force by the object, which is the Earth. This is because the object would not be in an orbit if those forces were not equal. It would, if the gravitational force was stronger, then it would just fall into the Earth. So it needs to be equal to each other for it to remain in an orbit. Now to find the kinetic energy this object has, due to its velocity orbiting the Earth, can be found by equating centripetal force with gravitational force. And we know the formula for centripetal force is mv squared over r, and we equate it to gmm over r squared. And since kinetic energy is half mv squared, then we say 2 times kinetic energy over r is equal to this. And basically after some simplifications, we get this equation for the kinetic energy. And so we have 2 equations now, one for the gravitational potential energy of this object here. So the gravitational potential energy is from h, from the center of the Earth, and the kinetic energy is due to the velocity it is orbiting with. Now in the orbit, We can also find the orbital speed. So again, this will be the same concept, equating the centripetal force with the gravitational force, because we're looking at the same scenario here. But all that we're doing is finding an equation for V rather than an equation for EK, which is kinetic energy. So all I've done here is equate these two and cancel out the like terms, and we get V squared equals gm over r, and so V equals root gm over r. So this is the orbital speed, the speed at which the object is orbiting around the Earth or any other object that's causing the gravitational field. Now there's also such thing as the escape velocity. So the orbital speed is the speed required for that object to stay in orbit, and the escape velocity is defined as the speed required for that object to have to be able to leave that orbit, to escape that orbit. So how we find this is by equating the gravitational potential energy with the kinetic energy. So we know this by the law of conservation of energy. The energy gained would equal the energy lost. So the gravitational potential energy is the energy gained, and the energy lost would be the kinetic energy at its leaving its orbit. So if the gained equals the loss, then the total should equal 0. So all I've done is said that gravitational potential energy plus kinetic energy equals 0. So we just sub in the respective formulas, and remember, keeping the gravitational potential energy is minus. And all I've done is now bring this over to this side and equate these two and cancel out the like terms, which in this case is m. And then we get the formula V equals 2gm over r all rooted. So now we can see here that these two formulas are quite similar, except this is just multiplied by 2 as 2 gm, and this is just gm. So we know that the escape velocity will always be bigger than the orbital velocity, which makes sense because the object would obviously require a larger velocity to be able to leave the orbit than stay in the orbit. And it would require a larger velocity because it needs to fight the gravitational force of the larger object, such as the Earth, that is keeping it in its orbit. So now let's move on to another part of orbits that you need to know for A-level syllabus, which is geostationary orbits. Now geostationary orbits are just one of the many orbits that satellites follow orbiting around the Earth. So when we have the Earth here, so there's many satellites orbiting the Earth, and all of these orbits have a certain name. And one of the orbits is named as the geostationary orbit, and this orbit actually has quite specific properties. So it is an equatorial orbit, which means that it orbits the Earth around the equator. And we know the equator is right around somewhere around the middle. So this orbit is basically orbiting around the equator of the Earth. And the second thing we know about this orbit is that the period is exactly 24 hours, and this is because the objects that are in this geostationary orbit have the same orbital speed or the same angular speed. The only difference between angular speed and orbital speed is that with orbital speed we're only referring to the magnitude of the speed, but with angular speed we're also referring to the angle at which the object is orbiting around. But the orbital speed and the angular speed is the same as the Earth, which is why the period required to complete a full orbit in this geostationary orbit is 24 hours. And the third property of this orbit, or the third thing we know, is from west to east. So this orbit is from west to east, which is the same direction of rotation as the Earth. So we know that the Earth is rotating from west to east, and that's how the objects in this orbit would also rotate. So that is just a small section on geostationary orbits that you need to know. Next, we move on to a concept known as weightlessness. Now, weightlessness is basically just a sensation felt when the centripetal force is equal to the gravitational force. Now, if you've seen many videos of astronauts that are in these satellites and they experience this floating, so they experience floating or something known as weightlessness. You probably might have also heard NASA has this machine that helps you, that sort of replicates the sensation of weightlessness, and this is basically due to the fact that the centripetal force is equal to the gravitational force. So when these satellites are spending their time in space, so when these astronauts are spending their time in these satellites that are orbiting around the Earth, the centripetal force of that circular motion is equal to the gravitational force that the satellite experiences. And so the resultant force between those would have to be zero. And when you have the resultant force zero, then the reaction weight, which is the resultant force that we feel on the surface of the Earth, for example, when we're standing on Earth, the weight is the resultant force that's acting downwards. But since there is no resultant force in this orbit, then there is no reaction weight. And so there will be no resultant force felt, and so the astronaut would basically float. So that is a concept of weightlessness that you have to know for your syllabus as well. So let's look at a graph that shows what happens between two masses and the field strength between those two masses. So on the y-axis we've put here the field strength, and on the x-axis is the distance between these two masses. So this point here is the position of mass 1. So if you're looking at a point here and moving towards mass 2 as x increases, so this is basically the range of x. As you move from mass 1, the gravitational field strength is slowly, gradually decreasing until it reaches 0. So at the midpoint here, the gravitational field strength at, x equals 2, x divided by 2, the midpoint, would be 0. Because if we were to draw our field lines, we would see that this is basically like putting two, for instance, positive charges together. In the midpoint, since they are sort of repelling each other, these field lines cancel out at this midpoint. So in the middle here, you would have no field strength. But as you go closer and closer to M2, if this point moves from M1 closer and closer to point 2, then the field strength would keep increasing until it reaches the surface. So this turns out to look like sort of like a cubic graph when you're plotting field strength against x, the distance between the masses. So that is one graph that you should keep in mind. Now let's look at the potential against distance graph. So now we're looking at the same situation with two masses, M1, or actually since I've labeled it as the moon and the earth, then I think it's best to draw that. So if we have the earth here and then the moon here, and we're finding the potential as the distance increases. So we're starting off from the Earth's surface here. So starting off from this point, the potential would be the most negative at the Earth's surface, and then you go out, you are doing less negative work, so the potential becomes more and more less negative, because as we know that coming into the earth you're doing more negative work, and so going out of the earth you will be doing less negative work. So it's gradually increasing until it reaches the moon's surface, And when it comes close to the moon's surface, the potential will become negative again, because now the moon's gravitational field is causing the potential, and so there's negative work done again. But as you can see, this graph is not symmetrical because the Earth has a very, very large mass compared to the moon. So the potential and the Earth's surface will be way more negative than the moon's, because there's way more negative work done, because the gravitational field strength is much stronger because the mass is bigger. So I hope you can see how that graph draws out and why it draws out like that. So let's look at some other graphs of just looking at a singular mass by itself and not just two masses. So if you have this mass here, let's label it as M. As you go away, so the gravitational force, this is F, gravitational force, would also start decreasing, because again the gravitational field lines will become less and less dense, so the gravitational force would be less, but it would never reach zero, because that concept is only when you bring your point to infinity, and since infinity is not really a real thing, it's just a concept to visualize certain aspects of the ideologies, then we know, so this will not reach zero, but it will come very, very close to zero. So that is how this graph sort of comes out to be. And if you're looking at the potential, then at the surface here, the potential would be very, very negative, and as you go out, it will become closer and closer to zero, because you are doing less negative work, as I explained earlier. So that would be the potential of a singular mass. And then the last graph we have to look at is the field strength of a singular mass. So again, this is similar to that of the force, but except the field strength starts off with the radius at the surface of the graph, because there is no field strength inside the sphere, inside the mass. So it will start off with at the radius, and then again decreases as you go further and further away from the mass. So that is all the graphs you need to know, and that is in fact all you need to know for gravitational fields for A-level physics. I hope everything I've said is clear, but if I have to clarify anything, please leave a comment down below or do email me, which is in the description. And yeah, I hope this video was helpful for you, and I'll see you in the next one. Bye.